Okay, and his title is Exploration of Initial State in Gravity via Entanglement. Please start.
Thank you for the introduction, and thank you for having me. It's my pleasure to coming back to Kyoto every time. Today I'm going to talk about my work in progress, which I expect to appear in April. So the last 30 years, so we have seen great advance in understanding of gravity. So there are two questions. The first one is where do the gravity degrees of freedom live in quantum gravity? And the second one is how to extract these degrees of freedom. And in this talk, I will apply these recent development on these questions to the following questions. So I will apply to the question how can we learn about initial state in gravity from the present universe, and I will ask the question of how this entanglement entropy and so on can probe the initial state of a universe, or how the entanglement entropy will be get large correction from the gravity and the initial state. So for the first question in the gravity, the important thing was the holographic principle. The holographic principle says that the gravity degrees of freedom in the space-time region is actually living at the boundary of the space-time. The most manifest and clear example of this is the ADS-shifty correspondence. So in the ADS-shifty correspondence, the gravity on the ADS space is actually equivalent to the conformal field theory at the boundary of ADS. So it's the holographic principle can specify where the degrees of freedom of gravity lives. And the more recent advance in the field of gravity is the entanglement reconstruction. It tells us where and how the degrees of freedom or excitation in gravity can be extracted from boundary CFT. So more precisely, consider ADS CFT and consider the subregion A at the boundary of the ADS spacetime, so that it's a subregion in the CFT. And consider the Liu-Takane surface corresponds to this subregion A. So as we know that the entanglement entropy of the subregion A can be computed by Liu-Takane formula, or it is a counterpart in generalized entropy, the FLM formula. And if you look at the region surrounded by A and the RT surface, this region is called the entanglement wedge. And the interesting feature of this subregion is that at leading order and Largen expansion, this entanglement wedge is actually dual to the subregion A of the CFT. So it's a duality between some region in the ADS and the subregion in the CFT. More precisely, the entanglement reconstruction tells us how to consider this mapping between bulk state and the boundary state. So Carry N correspond to the map from the bulk state to the boundary state, and the recovery map Carry R represent the map from boundary state to bulk matter state. So in this reconstruction, entanglement reconstruction, the key formula is a JLMS formula. It says that bulk relative entropy is equal to boundary relative entropy, and the leading order is Largen expansion. So this equality between relative entropy basically says that if you map the bulk state to the boundary state, there's no information is lost. It's a without loss of noise, you can recover. You can map the state, bulk state to the boundary state. And indeed, this is the very condition. The PETS recovery map is an exact recovery. So namely, the PETS recovery map maps the boundary state to the corresponding bulk matter state. So this bulk JLMS formula is the foundation of the entanglement reconstruction. And this entanglement reconstruction was also the key to the recent resolution of Hawking's black hole information paradox. So in this resolution of the paradox, you first consider a black hole, which is evaporating, emitting Hawking radiation. And you consider the reservoir A, which collected these Hawking radiations. So when you collect a lot of enough amount of Hawking radiation, so that the reservoir A is very much entangled with the black hole, the island formula tells us that the entanglement entropy of the subregion get a large correction from gravity. And island formula tells us that we must consider the entanglement island in the black hole, and the entanglement entropy should be computed by the area or the boundary with the entanglement island. The basis of this formula comes from that if you consider the up and down spins in the matter theory, you would think that they are orthogonal to each other. But if the theory is include gravitation, there's actually the small gravitationally suppressed overlap between these seemingly orthogonal states. And when you collect a lot of these such qubits in the reservoir, then the entanglement entropy will get large corrections, and the island formula capture this corrective behavior in a successful manner. And the entanglement island story can be okay. So entanglement reconstruction comes into the entanglement island story in the following way. So you can rephrase the Hayden-Presque protocol in terms of entanglement island in the following way. So in a modern terminology, the entanglement island is actually the entanglement wedge of subregion A or reservoir A. And so what it means is if you throw some small book which doesn't affect the background geometry after page time into the entanglement island. So what it means to be, what entanglement island is in the entanglement wedge means is that you can, if you look at the reservoir, which is outside the black hole, And with a smart quantum computer, you can actually recover the contents of this book from the reservoir A. So entanglement reconstruction is basically, you can reconstruct the information inside the entanglement from, even if it is non-locally separated. So the objective of today's talk is to apply this recent development to the following question. So the question I'd like to ask is what's the entanglement entropy looks like at the late time slice in universes with given initial state or boundary conditions. So the question is whether the entanglement entropy at the present time slices get corrected from the gravitation or initial conditions. So I will work in the JT gravity on ADS or De Sitter space, and I will turn off the gravity at late time. So it will be glued to the Minkowski spacetime. And I will impose some explicit initial conditions and the initial state for matter state. And in particular, I will not invoke the bracket wormhole, which connect the bracket. And I found that entanglement entropy, the last subsystem, is given by the boundary entropy or by the island formula, which I will explain in more detail in the following discussions. And also the objective of my work is to study reconstruction scheme for initial state in gravity, but this is work in progress, and I will not explain in detail. So let me explain the setup in more detail. So I will consider JT gravity on the Sitter space or Euclidean ADS spacetime. And matter, it will be the conformal matter. So the right picture is the gravity glued to some flat Minkowski spacetime. So P is the initial time slice or past time slice, and F is the future time slice, which connect gravitating region and the Minkowski region where the gravity is turned off. And I will fix the canonical variable, independent canonical variable, JT gravity, on this past initial surface P. And I will assume that P is in the positive imaginary time. So it's as in the Hartle-Hawking state. And I will consider matter initial state as a regularized boundary state. So what's the good about this regularized boundary state is the following. So regularized boundary state is a pure state. It has no entropy. It's a pure state. But if you take subregions, it actually looks like a thermal state with inverse temperature, beta. And this state is also at the UV approaches to the vacuum state. So if you consider the very, very small system, which is much smaller than the temperature scale beta, then it is same as the vacuum state. And also interestingly, the entanglement entropy of this regularized boundary state is given by the boundary entropy, and it doesn't have the kinematical entanglement. It's just given by the constant in 2D CFT. And it also models a global quantum quench, which is the global quantum quench is changing the Hamiltonian at some time slice suddenly to different Hamiltonian and consider the time evolution. So in the future time slice F, I will glue Dositta space or ADS space to Minkowski space with some boundary gluing condition. And what I will consider is the entanglement entropy of subregion A in this flat region. So these are the results. For small subsystem, it's the entanglement entropy is the same as that of the thermal system. It obeys a volume law with inverse temperature, which depends in the detail of the theory, and it doesn't matter in this talk. So delta L is the length of the interval A. So naively, if L goes to infinity, it grows linearly forever. And what happens for the subsystem is actually this entanglement entropy is saturated to at some value. So at the subsystem, either island phase or boundary phase will be realized. The island phase is the following, the left picture. So we'll have the island in the gravitating region. Here, this dotted line corresponds to separating a Lorentzian region and the Euclidean region in the past. And the island is in the Euclidean region. So in terms of CFT language, the twist operators are contracting with those of island, which is a emergent twist operator from gravitation. And the boundary phase, we have the twist operators are contracting with the boundary state. So I use the initial state, I use this boundary state. So in CFT sense, there's a boundary at the past time size. So this twist operator for the subregion A is contracting with the boundary of the initial state. In both scenarios, the entanglement entropy is bounded from above by the area bound in the past universe. Let me be more specific. So in the island phase, so this phase is realized when the area is smaller than the boundary entropy. Boundary entropy is defined by the Patchon function with a boundary. And in the JT gravity, the area is replaced by the value of diatom. So you can think of this area term as just a Dositta entropy. And the entanglement entropy is given by the roughly given by the Dositta entropy for the large subregion. So I'm currently working on the entanglement reconstruction of this setup, which is work in progress at the moment. So for those who knows about the bracket wormhole, you'll be worried about this such setup will violate strong subadditivity. The strong subadditivity is satisfied by imposing the following condition on the initial state. So the condition is, let's consider the CFT C plus C tilde which is factorized, which is a tensor product of two CFTs. And assume that one of the CFT has a much smaller central charge. And consider the reduced density matrix of this initial state, which where I trace out the larger CFT, CFTC, and consider this that it is entanglement entropy. The condition, or the condition that's strong enough to support the strong subadditivity, is that this entanglement entropy is the same as the thermal value, the thermal entropy of the CFTC tilde. In the boundary phase, this is realized when the area is larger than the boundary entropy. In this case, the entanglement entropy is given by the boundary entropy. And I expect the subset of degrees of freedom on the boundary can be reconstructed from A, but which is work in progress. And a special nice example of this boundary phase is the bracket wormhole. So suppose that's very special case where this boundary state has again the gravity dual, and gravity dual is actually given by the wormhole connecting bracket, which is described in the right figure. So the blue thing is our original JT gravity, and this black-blue line corresponds to the boundary state. And I'm assuming this boundary state has a gravity dual, the red region, which connecting two boundary states. So if this is the case, this is very similar to the bracket wormhole. And if you consider the subregion in Minkowski region and consider entanglement entropy, then you'd expect the island forms in the middle of the wormhole connecting bracket, which is basically the bracket wormhole. So in this case, entanglement reconstruction is rather manifest, so that the excitation on the island can be reconstructed from the state on the subregion A. So I'm expecting a similar thing happens in my examples, but they are still work in progress. So this is my summary. So what we did so far, is the following. So I consider the entanglement entropy of large subregion, and so that for the very large subregion, it gets large correction from gravity or the initial state. Each corresponds to the island phase and the boundary phase. And they saturate, well, not saturate. So one thing to note is that we are considering the entanglement entropy of a subregion in the flat space. So the area bound of present universe is trivially satisfied, but it is, in our case, it's probing the area bound in the past universe, where the cosmological constant is more larger. And our setup is kind of generalizing Hutto-Hawking no boundary proposal by adding additional boundary. And some nice feature about our analysis is that this basically applies to generic spacetime without wormholes as a background, but of course with the replica wormholes to compute entanglement entropy. This is good because it's non-Euclidean wormhole solution in higher dimensions are known to be unstable for instance, to the anti-brane nucleation. It is interesting to think about what's the choice of contour. So so we have considered the semi-classical geometry in complex geometry, but so you do worry that it's very weird type of setting. But if you consider the path integral via reference symbols, the path integral of the gravity with real metrics can be translated into the complex semi-classical geometry. So in this sense, it's not necessarily the weird things. That's all I wanted to say for the moment. Thank you for listening.
All right, thank you very much. Any questions or comments? Please raise your hand if you have. All right, please go ahead, Jisha.
Hi, thank you for your wonderful talk. I want to ask a very naive question. So it seems to me that in your island phase, the island region I and the original subsystem A is separated time-likely. Is that correct? Like
so
why?
The island region is in the Euclidean region. So the spacetime I'm considering started from the Euclidean signature, and it's continued to the Lorentzian signature.
I see. So in the Lorentzian signature, they are separated time-likely.
In a sense, yes.
Like I want to ask how is that how that happens, because when we talk about islands, it is usually space-likely separated from the original system, and then consider some entanglements like of original system and the islands between I'm sorry, and the complementary system. Then in this case, how should we like understand the relationship between the islands and the original system?
Okay, so in terms of just from the viewpoint of just a computation, it's just a analytic continuation of space-like separated correlator to time-like separation. And in more physical sense, for instance, if you so if you consider this bracket wormhole example, you can consider the bulk state, which is similar to the Thumb-Hill double state connecting I and A. That is a reasonable state. And you can consider the entanglement reconstruction of such state. Iron from
I see.
Excitation on I from A. So
I see.
So from the computation side, it's you have to sum over Bra and Ket contributions. So each one can be complex, but after summing up, it's become real.
I see. Thank you very much.
Whether you are MS.
Yes, I think that makes sense for me. Thank you very much.
All right, Numasawa-san, please go ahead.
Yeah, maybe it is related to this year's question. But so, generically, so does in your computation does it allow some Lorentzian interpretation, or for example, if we consider doubly holographic setup, then so the RT surface always stays in the sum, or okay, so can we, so RT surface exists in the Lorentzian spacetime?
So in this setup, we always have to consider Schwinger Tikevich type discussion of the surface, discuss gravity dual, and it's the same thing applies in this case as well. So you.
So for example, in island phase, do you need, maybe so you already asked in this education, but so do you find some like island on the Bra region and Ket region, and so do you need to take some of
Yes, in my case, you have to.
Or in other words, so is there something like a symmetry breaking for RT surface?
Also, I'm always summing up contribution, and each for Ket side, they are complex, and Bra side it is complex conjugate, and after summing up this two contribution, I get the real positive entanglement entropy.
So then, yeah, so again, so maybe I'm going back to the first question. So is there no Lorentz, pure Lorentz signature, Lorentzian interpretation?
Of what situation are you considering?
For example, so in the last picture, so this entanglement interpreted as some entanglement between the Hilbert's CFT on a flat region and this some bracket wormhole region. And I wonder whether we can interpret always in such a way. In this case, so we can interpret this as computing some entanglement between the flat space CFT and CFT on a closed universe with the contribution of the area. I wonder whether we can interpret entropy in such a way.
Yeah, so I'm expecting similar somehow double structure will appear in my setup as well. But at the moment, I don't have something concrete to say about it.
I see. Okay. Yeah. Thank you.
Yeah. But okay. So as long as you have the Euclidean region in the past region, you can always consider something similar to the somehow double-like state.
I see. I see.
So I expect that's what can happen, what will happen. But I have to be precise about how to define the reduced density matrix and so on.
Okay. Yeah. Thank you.
Okay. Any other questions or comments? If not, let's thank the speaker for his nice talk. And it is the end of the morning session, and the afternoon session will start from 2 p.m. in Japanese time. And before closing session, there will be an announcement about remote session during the lunch time from Ugajin-san. Could you start the announcement?
Oh yeah, just put the link, to the chat. So if you are interested, you can use it. Yeah, that's it.
All right, thank you very much. Any other announcement from Takayanagi-san or any other people?
I don't have.
All right, then let's close this session. Thank you very much for attending.
高柳さん、ホストも一旦高柳さんに移してますんで。
わかりました。じゃあ私の方で。
はい、都合のいいときにお願いします。
Thank you very much for participation and we'll start again 2 p.m. and I will close